In this lecture, we're going to be talking about geometric optics. We're going to be talking about light in terms of light rays propagating through space, and we're going to talk about how that works out in the situation where you have mirrors or lenses. Mirrors may be curved, and there's a good deal of geometry involved, so let's begin. The basic law that we're going to start with for our investigation of mirrors is the law of reflection, which we saw last week. The incident ray strikes a plane surface, it reflects away in the direction of the reflected ray, and the angle of incidence, the angle between the incident ray and the normal, is equal to the angle of reflection, the angle between the reflected ray and the normal. And that's pretty straightforward, and we saw how that can lead to the formation of an image. If you have an object on one side of a mirror, then light rays coming away from the object will reflect away, and if you think about it, you can say these reflected rays appear to come from a point behind the mirror, and that point behind the mirror is the location of the image, the place where the object appears to be due to the reflection of light by the mirror. Okay, so let's work this out a little bit geometrically. Let's imagine you have an object, and we'll consider two particular rays, the object sitting on what we might call the optical axis, and the mirror is perpendicular to that axis, and we imagine two particular rays from the tip of the object. One goes straight to the mirror, hits the mirror at normal incidence, and reflects straight back. And the other one heads to the mirror and hits the mirror at the optical axis and bounces again with the law of reflection back downward. And if you trace these two rays back, you can find their point of intersection, and their point of intersection is the location of the image. Now, it's pretty easy to see that the object distance S, well, first of all, the object distance is called S, and it's the distance between the mirror and the object, and we'll call this distance positive if the object is on the side of the incoming light. And you might think that's always going to be true, but a little later on in class we might see an example where it's not. And then there's the image distance, and the image distance S prime, and we're going to say that that distance is positive if the image is on the side of the light that's going out. Now in this case it's not. In this picture the image is not where the outgoing light is. The image is behind the mirror where there is no light. And so this image distance here is negative. And in fact you can see that in this case for a flat mirror that the object distance and the image distance must be negatives of each other. Now, so much for a flat mirror. One other thing you might notice is that the object and the image are the same size in this picture. They won't necessarily be later on, but if we take y equal to the object height, which is generally positive, y prime is the image height, and it's positive if the image is in the same direction, but if somehow the image were upside down, if it were inverted instead of being upright, it would be negative. And the magnification is the ratio of the size of the image distance to the image height to the object height. It's y prime over y. In this case, the magnification of a plane mirror is obviously +1. Okay, what about a curved mirror? What if the mirror is and we're going to talk about a concave mirror, a mirror that's curved with the concave surface toward us. And in class we'll talk about the other case. Well, we're going to make two assumptions about this mirror in order to analyze it more easily. One is we're going to assume that the mirror is a section of a sphere of radius r, that it's a spherical mirror. And the second assumption we're going to make is that it's only a small part of that spherical mirror. In other words, the mirror's curve is very shallow. It's essentially, we can think of the mirror as all being in one plane. Although it is a section of a sphere, it's a fairly small section of a sphere. The size of the mirror that we care about is small compared to the radius of the sphere that the mirror is a section of. The textbook sometimes calls this the paraxial approximation, but in this case it's really the shallow mirror approximation. Okay, so the mirror is essentially all in one plane. So let's look at how the light from an object might reflect off of a mirror. And there are a couple of situations where it's pretty clear how that will happen. If light from the object goes through the center of curvature of the mirror, the center of the sphere that the mirror is part of, then it'll bounce straight back because that will be along a radial line of the sphere, and so that ray will bounce straight back, passing right through the object. And the other ray that is easy to figure out is a ray that hits the vertex point. That is to say, the place where the optical axis hits the mirror. At that point, the mirror is vertical, so it's just like a vertical plane mirror, and the reflected ray is the same angle below the axis that the incident ray is above the axis. And the place where these two constructions intersect is the place where reflected rays will appear to be coming from. That's the location of the image. You can see that this image is in front of the mirror and it's upside down, and it's smaller than the object in the case that we've drawn. So now we're ready to do a little geometry. So what we're going to do is we're going to set up the problem so that this curved mirror, this shallow mirror, is actually a plane in our diagram. And we draw the light rays, and the diagram looks something like this. We see the object and the image, we see the light rays, we see the mirror over on the right-hand side. S is the object distance. S prime at the bottom there is the image distance. R is the distance to the center of the sphere. And y is the height of the image. Y prime, y is the height of the object, rather. Y prime is the height of the image. It's actually negative because the image is inverted. So there are a couple of triangles in this diagram which are very interesting. So for example, consider these two triangles formed by the object and the image and the vertex of the optic axis. These are similar triangles because of the law of reflection, and so we can tell from these triangles that the corresponding ratios of sides should be equal. So the absolute value of y prime being negative, of course, over s prime is equal to y over s, which means that the absolute value of y prime is just y times the ratio s prime over s. By the way, this also means that the magnification, that ratio of y prime over y, the magnification is the negative of the ratio s prime over s. Okay, so that's one useful relation between the y prime and y and s prime and s. Okay, now let's look at another pair of triangles. This pair of triangles formed by the object and the image and the center of the spherical mirror. Once again, we have two similar triangles. They're similar because they're both right triangles, and they have the same angle there at the center point. And so we can equate a ratio for the large mirror, which is s minus r, the length of the leg, over y, the length of the other leg, and that's going to be equal to r minus s prime. That's the length of the leg along the axis for the image triangle, over the absolute value of y prime. And given that we already figured out an expression for the absolute value of y prime, we can write that as r minus s prime over y times s over s prime. So to figure out what to do with this relation, we need to do a little algebra. The first thing, of course, we're going to do is we're going to cancel y, multiply both sides by y. The height of the object doesn't matter, and we just get a relation between the image distance and the object distance and r. And then we're going to divide both sides by s, and that makes it look very symmetric. We get s minus r divided by s is equal to r minus s prime divided by s prime. Of course, we can rewrite each side. On the left-hand side, we get that 1 minus r over s is equal to, and then on the right-hand side, we get r over s prime minus 1. Now we collect the ones on one side and the s prime on the other side. So let's add 1 to both sides and add r over s to both sides. I'm going to write it in backwards order, but you'll see it very simply. On this side I have r over s plus r over s prime. That's going to equal to 2. 1 plus 1. Okay, what does that tell us? If we divide both sides by r, we get the following very elegant relationship. 1 over s plus 1 over s prime is equal to 2 divided by r. That's the relation between object distance and image distance for a spherical mirror. So that gives us a kind of a spherical mirror equation which we can use to figure out where the image would appear in a particular problem. And we can write it in an even neater way by defining the focal length of the concave mirror to be the radius of curvature of the mirror divided by 2. The focal length is just r over 2. And that gives us a very elegant expression that 1 over the object distance plus 1 over the image distance is 1 over the focal length. This, by the way, contains the flat mirror equation as a special case, because in the flat mirror equation, the radius of curvature is infinite, so the focal length is also infinite. The reciprocal of the focal length is 0, so that means that s has got to be the negative of s prime, so that this spherical mirror equation works out. All right, let's work out a specific numerical example. Let's suppose that the radius of curvature of our mirror is 20 centimeters, and our object is 50 centimeters away from the mirror. What is the image distance? Well, the focal length of the mirror is just half of the radius of curvature, 10 centimeters, and so when I solve my spherical mirror equation, 1 over s prime for 1 over s prime, that's 1 over f minus 1 over s prime. 1 over f is 1 over 10 in inverse centimeters. 1 over s is 1/50th, and I wind up showing that that s prime is 12.5 centimeters. And that looks like it could be right in the diagram. Furthermore, I can work out the magnification, the ratio of sizes. The magnification is the negative of s prime over s, we decided, which is the same as y prime over y, and that's minus 0.25. So the image is 1/4 the size of the object, and is inverted. That's what the minus sign means. Let's look at another extreme case. Let's suppose you had a very distant object, an object that was maybe as far away as the sun. Maybe it is the sun. In any case, the object distance is practically infinite. So that means that the incoming rays from the object are essentially parallel. They diverge from a point on the object, but that point is so far away they're essentially parallel. Well, what happens? Well, what happens is that the image distance becomes the focal length. So all of the rays converge on the focal point, on the focal length from the mirror. That's why it's called the focus. And if you put something there, then you would be able to collect that all that light at a particular point. So this is why we use concave reflectors for reflecting telescopes and for high-gain radio antennas, radar antennas, and so on, because of this property of taking very distant rays and focusing them all at one point. Now, in mirrors, we've seen two kinds of images, which we can call real images and virtual images. Now, both of these are images. Neither of these are real objects. But a real image has an image distance greater than 0. That is to say that the image is located on the side where the outgoing light rays are. The light rays pass through the image point. The image point forms, in the case of a mirror, in front of the mirror, between you and the mirror. That's where it looks like it is. And the image is always inverted. A virtual image has an image distance that's less than 0, that's negative, and that's behind the mirror. The light rays don't actually pass through that point, but the image is upright. So we have a real image or a virtual image. So what we're going to be talking about next is what happens when light passes through a transparent medium, and we'll talk about lenses and things like that instead of mirrors. And that's, of course, all going to be based on the law of refraction, Snell's law, which we talked about last time, that the index of refraction of medium A times the sine of the angle from the normal on the A side is equal to the product of the index of refraction in medium B times the sine of the angle from the normal on the B side. So there are lots of interesting applications of this. The simplest application has to do with the apparent position of an object, let's say underwater. So we've got the air and the water, and the object is at some depth in the water, and the light rays come from that object, but they're refracted at the surface. And so the object appears to be not as deep as it really is, but at a somewhat shallower depth. So how deep is it? Let's do the analysis. So what we're going to do is we're going to construct something like this. We have the vertical ray, which just goes out from from the object, and also appears to be coming from the image. And we'll look at another ray at an angle theta sub b that is refracted to the angle theta sub a as it passes into the air. And the point of intersection of those two refracted rays, if we trace them back, is the apparent depth d prime of the object. D is the actual depth. Okay, so to work this out, I want to first make an approximation. And the approximation is that I'm going to imagine that theta sub b is really small, and theta sub a also. That although I've drawn them pretty big, I want to consider the situation in which I'm looking at rays that are all nearly vertical. So it's as if I'm looking almost straight down into the water, and the only rays that I see are rays that are nearly along that vertical line. And so if those angles are small, then it turns out that the tangent of the angle is about the same as the sine of the angle. It's a very convenient approximation. Now, if you look at the diagram, there's a line on the surface between the two rays, and that line is the same in two triangles formed by the image and the object, and those two triangles, that length will be d prime times the tangent of the angle is equal to d times the tangent of the other angle, the angle theta sub b. And if I solve that for d prime, the apparent depth of the object, then that's d times the ratio of the tangents of the angles, but the tangents are about equal to the sines, and so that's about d equal to the ratio of the sines of the angles. But the ratio of the sines of the angles will be the inverse ratio of the indices of refraction by Snell's law, and that means that the apparent depth, d prime, is about equal to the depth times the ratio NA over NB. Now let's suppose this is air and water, then NA is about 1, and NB, the index of refraction of water, is about 4/3, so NA over NB is about 3/4. So the apparent depth of the object is only about 3/4 of the actual depth of the object. Okay, so now we're ready to analyze lenses, and we're going to focus our attention on thin lenses. That is, and what do we mean by a thin lens? Well, of course, as rays pass through the lens, they're refracted and they change direction. But we're going to assume that all the direction changes occur at one plane in space, the plane right in the middle of the lens. And if the lens is pretty thin, this is a pretty good approximation. So all the rays change direction at the same plane surface. And we're going to consider a convex lens. I've drawn it as a doubly convex lens. It's convex on both sides. And that will tend to take rays and bend them toward the optical axis. Let me illustrate. If you have a bunch of rays coming in all parallel, then it will turn out that the convex lens will have the effect of bending those rays and causing them to converge at a point, a focus point, behind the lens, downstream of the lens, on the right-hand side in our diagram. And the distance of that focus point from the lens is called f, the focal length of the lens. And for a convex lens, a so-called converging lens, you can see why it's called that, f is positive. Where does that lead us? Well, let's suppose you have an object that's some distance away from a lens, and it has a focal distance of f. There are three rays that I can trace through this diagram that are really easy. And the first one is the ray that goes parallel to the optical axis from the object. And when it hits the lens, it's one of those parallel rays, and so the refracted ray passes through the focal point on the far side of the converging lens. The second easy ray actually passes through the middle of the lens, where it hits the optical axis. And there, the two sides of the lens are sort of parallel to each other. And although the ray might be deflected sideways a little bit, in fact, it's not changed. It doesn't suffer any net change in direction. So that ray just passes straight through. Now, these by themselves would be enough, but let's draw another one. And that's one that passes through a focal point on the left-hand side. And if you pass through that focal point, then on the other side you come out parallel to the axis. Note that in each case the light is deflected toward the axis. Okay, those three rays pass through a single point on the downstream side, the right-hand side of the lens. That's where the image is located. If you were off to the right, you would see light emerging from that point. That image is inverted. It has a height y prime, which is negative. It's located at an image distance s prime, which is positive because it's on the same side as the outgoing light. And so you have s and s prime and y prime, and you have a couple of lovely triangles you can use to figure out mathematical relations. The first one is a triangle formed by the image and the object and the vertex, the point in the middle, and these are similar triangles. And from this, just like before, we get a relation between y prime, y, s prime, and s. And it basically tells you that the ratio between the image size and the object size is the same as the ratio of the image distance and the object distance, with a minus sign because y prime is negative. And it also tells you that you can calculate the magnification by just taking the negative of the image distance over the object distance. All right, let's look at the other triangle, and that's this triangle formed on the left-hand side by the lower ray. The right-hand triangle, like the ratio of the two legs of the triangle, is s minus f over y, and that's going to be equal to f over the absolute value of y prime, which from our previous work is f over y times s over s prime. And so now we can take this and manipulate it just as we did before. We can multiply both sides by y and divide both sides by s. So we get s minus f over s is f over s prime. And then we can rewrite this and manipulate it just as before, and we get the following very nice equation. In fact, we get an equation that looks exactly the same as the equation we had for spherical mirrors. 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. And this is the thin lens equation. So we'll do applications. We'll do applications of the thin lens equation in class, and we'll do lots of problems, and there'll be some interesting and surprising wrinkles, and it'll be fun. But you might wonder where the focal length of the lens comes from. What determines the focal length of the lens? And the answer is the shape of the lens determines the focal length, together with the optical properties of the material, the glass or plastic or whatever, that forms the lens. So let's state the basic relation for this. This is derived in the textbook, but I'm not going to derive it here. I just want you to see it. It's very useful. And so let's look at the the cross section of a lens. Now this lens I've chosen so that both sides curve in the same direction. One of them curves a little more than the other one, but they both curve in the same direction. And so we're imagining light coming along from the left-hand side. And the first surface it strikes, that first surface, has a certain radius of curvature, R1. It's the radius of curvature of the first surface. And then it strikes, then it's in the glass, and then it comes out on the right-hand side of the lens, and it strikes that second surface, which has a different radius of curvature, R2. Now, if the radii of curvature are in this direction, they're both of the same sign. They're both positive. We can see, though, that R2 is a little bit larger than R1 in this case. It's a shallower curve, so it's a part of a bigger sphere. And finally, the material of the lens has an index of refraction of n. And when you put these things all together, you get the following equation, that 1 over the focal length of the lens is n minus 1 times 1 over R1 minus 1 over R2. Notice that if R1 and R2 were the same, the two sides of the lens would be parallel to each other. They'd be sections of a sphere of the same size, and the focal length would be infinite. It wouldn't really have a focal distance. Also, if the lens were made out of air, n equal to 1, then the focal length would be infinite. It really wouldn't act as a lens. This is called the lens maker's equation for a thin lens, and it's a very useful relation that for figuring out the optical properties of a thin lens of a given shape and an index of refraction. Okay, so that's a first look at lenses and mirrors, and we'll work out many more of the details in class and work a lot of good problems. And in fact, a little later in the semester, you'll have a laboratory where you'll do some experiments here. So it's off to studying lenses and mirrors this week. See you in class.